We will now be moving on to Unit 3, and this is our introduction to Chapter 5. It says, just as a reminder, a random variable is a numerical measure of the outcome from a probability experiment. So its value is determined by chance. Random variables are denoted using capital letters, such as X, and then remember a random variable is said to be, first, a discrete random variable if it has either a finite or a countable number of values, or two, it could be a continuous random variable if it has infinitely many values. And remember that usually these things are counts of something. And we dealt with a lot of discrete random variables in Chapter 4. And then down here, many times these are measurements. And so that's kind of our guidance as we look at these two and how we tell the difference between the two of them. Example 5.1, the values of a discrete random variable can be plotted on a number line with space between each point. The values of a continuous random variable can be plotted on a number line in an uninterrupted fashion. In other words, it's kind of like that idea, if you've got a discrete situation, you know, again, if we're kind of thinking about that idea of a count, you might have 0, and then you might have 1, and you might have 2, and 3, and so on, but you can see there's space in between each of these dots. Whereas if you're doing continuous and you're measuring, you know, let's say just something simple, we're measuring a segment. Well, that segment could have this length or this length or this length, and there's no, you know, 1, 2, it could be 1.5, it could be right here, this distance, and so there's all these decimals and stuff in between, so there's no gap in between these values. You just have, it could be here, it could be here, it could be here, it could be here, and so all these dots that you're writing down connect with each other, and that's why you're able to plot that in an uninterrupted fashion. Example 5.2, determine whether the following random variables are discrete or continuous. State the possible values for the random variable. Letter A, the number of light bulbs that burn out in a room of 10 light bulbs in the next year. All right, well, let's assume here that you're not replacing them. This would be discrete. You're counting how many are going to burn out. And those values would be, could be none burn out, could be 1, could be 2, all the way up to maybe all 10 of them burn out. So that is our set of possible outcomes for letter A. Letter B, the number of leaves on a randomly selected oak tree. Well, again, you're counting the leaves. This is discrete. Number of leaves on a randomly selected oak tree. Well, if it's a winter, I suppose it could have 0 leaves. And then I don't know how many leaves would be on an oak tree. You could kind of go forever, I suppose, if it was a big enough oak tree. So you're talking about integers 0 and greater. Letter C, the length of time between calls to 911. Well, when you talk about length, even though it's time, you are measuring something. This is going to be continuous. And again, these are going to be values that are, we'll just say x. So x is greater than or equal to 0. I suppose it's possible that calls come in at the same time. Here we could say that's not a very good. We could say x values where x is greater than or equal to 0, but these are also integers. Here it's just any values that are greater than or equal to 0. You can't have negative time there, but that would be our answer to part C. The probability density function, which is abbreviated as PDF, is represented in the function notation f of x to represent the curve where f of x is the function that corresponds to the graph. We use this density function f of x to draw the graph of the probability distribution. So we did probability density functions in the last chapter, but we were dealing with discrete, so it was just individual values in a table. Here we're going to actually look at graphs when we think about these continuous situations. So we're going to use the density function like it says to draw the graph of our probability distribution. The area under the curve is given by a different function called the cumulative distribution function, abbreviated the CDF. The cumulative distribution function is used to evaluate probability as area. Properties of the continuous probability distribution. The outcomes are measured and not counted. So again, it's that idea of measurement compared to counting. Counting would be discrete, measurement is continuous. The entire area under the curve and above the x-axis is equal to 1. And we're going to find out why that is. It's because this area is going to match up with the idea of probability. So the probability must equal 1, and therefore the entire area must equal 1. Number 3, probability is found for intervals of x values rather than for individual x values. And that's going to be an important distinction here. When we were dealing with discrete values, we just said, okay, well, how many times does this occur? Or what's the probability of this one value occurring? Here we're dealing with regions of the graph. Number 4, the probability of x being between c and d, that's how you would write that, it's greater than c and it's less than d, is the probability that the random variable x is in that interval between the values of c and d. So the probability that x is between c and d is the area under the curve above the x-axis to the right of c and to the left of d. And we're going to draw pictures to represent that, but that's what that is talking about when you're talking about the probability that x is between c and d. Number 5, the probability that x equals c is 0. And the reason is technically because that one spot doesn't have any width, and so when we talk about area, it doesn't have any area. And so let's look at that. The probability that x takes on any single individual value is 0. Let me erase that line. The area below the curve and above the x-axis and between x equals c and x equals c has no width, and therefore it has no area. Since the probability is equal to the area, that probability is going to be 0. Number 6, probability again that x is between c and d is the same as the probability that x is between c and d, even if we include those endpoints c and d, because the probability again is equal to the area, and the area would be the same for either one of those. It doesn't increase the area at all. Having gone through that introduction, here we go with section 5.1, continuous probability functions. A continuous probability function is a continuous probability distribution with a cumulative distribution function that is absolutely continuous. That means there are no breaks in it. So that's what absolutely continuous means. It means there's no breaks in it. There's no part that there's a gap. There's nothing like that. It's got to connect from one point to the next. If the distribution of x is continuous, then x is called a continuous random variable. And the probability that x is greater than c and less than d is going to be equal to the area under the curve between c and d. So let me draw a picture of that because we haven't really seen a picture of that yet. So let's say that this is a very common distribution function that we'll use, the normal distribution. And let's say that this is the value c and this is the value d. So in this case, when we write it this way, we are making the assumption that c is less than d, or c is to the left of d. And so if we put like a boundary at c and another boundary at d, and we figure out this area in here, that area, which is less than 1, it's between 0 and 1, will be equal to the probability that x is between those two numbers, that the result of our outcome will be between those two c and d values, whatever those values are. So for example 5.3, let's consider the function f of x equals 1/20th for the values between 0 and 20. So this one is a pretty easy one to draw. Here's 0, here's 20, and 1/20th, if you think back to your algebra days, this is a constant. So I'm just going to put 1/20th here. And this function is always equal to 1/20th. And so if you think back to our types of graphs that we have, this is a uniform distribution. The probability is the same for everything, each individual value, where x is a real number. and construct a figure representing f of x. Okay, I guess I've already done that. So here's f of x. And we're going to find the probability that x is between 0 and 20. All right, well, that means that here's one boundary and here's the other one. What is the area that we've got here? Well, notice this shape is a rectangle, and this will take you back to a little bit of geometry. But the way we find this is we're going to take 1/20th, which is the value of this function, 1/20th for all of it, and then we multiply by the width that we're covering. Well, the width is always the bigger value minus the smaller value. And since we were told that the bigger value is 20 and the smaller value is 0, that's 1/20th times 20, which equals 1. And that hopefully makes sense because we are including the entire graph in our probability there, and the probability has to be always equal to 1. So that is our example 5.3. We're going to use situations similar to this, but usually we're not going to include the entire graph because that, in a real life situation, that kind of be pointless. So, but that's example 5.3. Example 5.4, let's take that same graph or the same information from 5.3. So 1/20th is our function, and it goes from 1 to 20, or sorry, from 0 to 20. And this time we're going to construct a figure representing f of x, and the area is going to represent p from 5 to 12. So let's just estimate a little bit. Here's 10, so here'd be 5, and then 12 would be about right here. So if we're going to do this one, we're going to have a boundary point, lower boundary point at 5, upper boundary point at 12, and we're looking for this area right here. Now, once we have that area marked off, we want to find how much is that area. So P of 5 less than or equal to x less than or equal to 12 will be equal to the height, 1 over 20. That's the height for this shape, times, and then we've got our width of our rectangle here, and the width is going to run from 5 to 12. So our width is going to be a total of 7 when we put that in. And we multiply that fraction together, we get 7 over 20. So that will be our probability for x being between 5 and 12. Once again, we're using the same situation. And we've got our 1/20th here. And it goes to 20. Now this one will be a little bit different. Construct a figure representing f of x, representing the area P from 2.3 to 7.5. So here's 0, here's 10. Again, we're going to estimate 2.3 is going to be about right here. And 7.5 is going to be about right here. The picture doesn't even have to be great, but just so that we have an idea. In fact, let me switch colors here again. And we're looking for x to be in that region right there. So the same thing we did before. P of 2.3 less than or equal to x less than or equal to 7.5 is going to be the height of our rectangle, 1 over 20, times the width of our rectangle, and that's always the bigger value minus the smaller value. And so in this case, it's 1/20th times, and what is that, 5.2? So 1/20th times 5.2 would be 5.2 over 20, but that's not a very nice fraction. So we don't want to have decimals and fractions mixed together. So let's just go ahead and take 5.2 divided by 20, and we're going to get 0.26. So that would be our probability that x is between those two numbers. So regardless of if you are dealing with integers or decimals, your height is staying the same in a uniform distribution like this. And then to find the width, you just take the bigger value minus the smaller value. In this case, that was 7.5 minus 2.3. And that will give you the width of your rectangle, and you multiply the base times the height or the length times the width, however you want to think about that. So note, in general, the area under the continuous probability function, f of x, where x has to be between c and d, between a and b. So we're finding the probability that it's between a and b. That's kind of confusing. I may have to rewrite that. It's given by area equals. Now I did these in reverse order, but here's our height. the f of x function, and here's our width that we're looking at. So notice in this case that your a and your b are inside your interval, and these are the total intervals here that we're looking at. So you would have your base, it's just, again, it's a rectangle. It's the width times the height, and to find that width and height, the height is given to you from the function, and then the width is, you have to figure that out from the endpoints that they give you to consider. That is the end of section 5.1, and so here are your graded problems, or you're going to have 5 graded problems from that homework. And again, get at that as soon as you can. If you have questions, please make sure that you send me a message and ask me about those.